30,000 tires disappear here every day. Yet the difference between a seamless transformation and a catastrophic shutdown hinges on a single overlooked step: extracting the steel bead. Miss this detail and entire shredding lines grind to a halt. Maintenance teams have recorded losses of €3,200 and hours of downtime from a botched bead. The real story behind mass tire recycling is not just scale. It is precision engineering, razor-thin margins, and hidden machine failures that could unravel the whole system. What really controls the fate of all those tires? Steel bead removal does not draw headlines, but it is the difference between a plant humming at full speed and a maintenance crew scrambling through the night. In the heart of the operation, automated bead pullers clamp each tire and rip out the steel core with hydraulic force. Every cycle is tracked by sensors and SCADA logs, watching for the telltale spike that signals trouble. When the bead is not fully extracted, whether from a deformed tire, a worn hook, or a moment's lapse in loading, the missed wire slips through. It is a silent error, invisible until the next stage. October 2022, Jennings' main line experienced a single incomplete bead that went undetected. The primary shredder's torque alarms flared as the hidden steel hit the knives. 3 blades shattered in minutes. Maintenance logs show 6 hours lost, €3,200 spent on emergency repairs and overtime, and the night crew's testimony still bristles with frustration. The incident is etched in the plant's records, with SCADA traces showing 3 torque peaks, each one a warning missed. The numbers are unforgiving. Every hour offline means up to 20 tons of rubber unprocessed, and each knife replacement is a costly scramble. Plants operating at this scale have learned the hard way. At least 95% bead removal is not a target. It is a survival threshold. Maintenance supervisors can point to the pattern. Every uptick in missed beads is followed by a spike in jams, downtime, and overtime bills. Modern stations now run multiple inspection checkpoints, with force sensors and cameras flagging incomplete pulls. Predictive maintenance routines swap out blades before they dull, and operators are retrained after every incident. The bead pull stage, often dismissed as routine, is the first and most critical line of defense. Without it, the entire process risks grinding to a halt, the cost measured not just in euros, but in lost hours and broken steel. Twin-shaft shredders stand as the next barrier against steel contamination. They are designed not for speed, but for controlled, relentless force. Each tire enters a chamber lined with interlocking knives, 40 to 80 millimeters wide, rotating at just 10 to 20 revolutions per minute. This deliberate pace is no accident. SSI and UNTHA engineers say the low rotational speed and robust knife geometry are tuned specifically to absorb the unpredictable resistance of tire rubber and any residual steel that escapes upstream. The result is a steady output of rough chunks, ranging from 50 to 150 millimeters, ready for further processing. Steel fragments remain a constant threat. Even with high debeading rates, up to 5% of tire steel can still slip through, embedded in bead wire remnants or sidewall cords. Here, the first line of magnetic defense comes into play. Overband magnets, suspended above the conveyor, pull free the largest ferrous pieces immediately after shredding. Drum magnets, positioned just downstream, target smaller fragments missed in the initial sweep. Together, these magnets remove between 10 and 30% of the total steel content in a single pass, a figure confirmed by plant audits and supplier data. This early capture is critical to protect downstream equipment. OEM representatives stress that this early-stage steel capture is not about perfection. It is about protecting the machinery that follows. The primary goal is to intercept the bulk of heavy metal before it can reach high-speed grinders, where even a single missed wire can trigger catastrophic tool failure. Multiple passes are standard practice because no single magnet can achieve the near total purity needed for downstream equipment reliability. Plants that cut corners on magnet staging routinely report doubled blade wear and unplanned stoppages. Maintenance logs show a direct link between residual steel and grinder downtime. The combination of slow, forceful shredding and layered magnetic separation forms the backbone of mechanical defense. Every design choice, from knife width to magnet field strength, reflects a hard lesson learned from past failures. As one EM representative puts it, the cost of a missed wire is measured not just in broken blades, but in lost hours and mounting repair bills. This stage sets the baseline for how much steel remains and how much risk is carried forward into the next round of size reduction. Chunks of shredded tire, still laced with stray fibers and traces of steel, enter the next phase, a labyrinth of machines designed to chase purity down to the decimal. Raspers and granulators, each fitted with screens narrowing from 20 or 25 millimeters down to as fine as 1 or 5 millimeters, tackle the material in stages. At every step, process engineers log particle size and fiber load, knowing that a single missed cleanout can derail an entire batch. The screens act as both gatekeepers and bottlenecks. If textile buildup clogs a mesh, the result is not just a slower line, but a risk of fiber contamination above the 0.5% rejection threshold set by most customers. Inspection routines here are rigorous. Operators record hourly checks, and they pull random samples to run fiber and steel residue tests. If a spike appears on the quality control chart, the line is paused for a full cleanout, and the event is documented in shift logs that track every incident. A 2023 report from a Northern European plant records a single overlooked cleanout that led to a rejected batch, with mass flow diverted and quality control frequencies doubled for the following week. These events leave a clear paper trail, Sankey diagrams showing diverted material, inspection checklists marked with emergency notations, and operator comments detailing the scramble to restore compliance. Beyond granulators, the AIR knife comes into play, a high-velocity jet that strips away liberated textile fiber and dust and sends it to collection hoppers. Cracker mills follow, breaking down any remaining fluff, while zigzag airtables push lighter fibers out of the stream. Each of these steps is paired with additional magnets and air cyclones, reinforcing separation at finer scales. Skipping a single cleanout or letting fiber accumulate can weaken the modulus of the finished crumb, turning a high-value output into a reject pile. For plants operating at 30,000 tires per day, the margin for error is slim. The process engineer's logbook becomes a critical artifact, capturing the discipline and precision required to keep fiber content below the 0.5% line and to maintain the purity demanded by downstream buyers. Grinding scrap tires into fine crumb is a contest of cost and quality. Two methods dominate the field: ambient grinding and cryogenic milling. Each brings its own set of numbers, energy bills, supply contracts, and the daily math of running a plant. Ambient grinding leans on electrical muscle. Hammer mills and pin grinders process rubber at rates of 120 to 200 kilowatt-hours per ton, depending on feed cleanliness and blade sharpness. For a facility handling 300 tons a day, that is up to 60,000 kilowatt-hours, an energy bill that lands between 10 and 30 euros per ton based on industrial rates. There is no need for special consumables, but the grid must be steady, and every tool change chips away at the bottom line. Cryogenic milling takes a colder approach. Rubber granulate is frozen to -80 degrees Celsius, or even -120 degrees Celsius, with liquid nitrogen, making it brittle enough to shatter. This process cuts fiber contamination by 22% compared to ambient methods, producing a cleaner, more angular crumb. But the logistics are relentless. Each ton of crumb requires 70 to 100 kilograms of liquid nitrogen delivered by tanker. For a 300-ton operation, that is up to 30 tons of liquid nitrogen daily, demanding bulk storage and a constant flow of deliveries. Liquid nitrogen pricing, shaped by contract and distance from the nearest air separation plant, typically runs 18 to 25 cents per kilogram. That adds an extra 14 to 30 euros per ton, on top of the modest electrical draw. Minutes from a 2021 pilot study capture the debate. Finance flagged the risk of liquid nitrogen costs, wiping out the savings from cleaner crumb and less tool wear. Operations argued for the quality edge, pointing to the 22% drop in fiber and smoother downstream handling. The data confirmed the technical gains, but the economics barely broke even at current nitrogen prices. Any spike in liquid nitrogen costs or delivery issues could erase the margin overnight. The choice is not purity versus power. It is a calculation of energy invoices, liquid nitrogen manifests, and logistics. Cryogenic milling delivers on quality, but its economics depend on contract terms and regional supply, shaping both cost and feedstock consistency for the next stage. Pyrolysis sits at the crossroads of chemistry and economics. Its design choices dictate what comes out of every ton of rubber fed in. At the heart of the process, reactor type and temperature profile decide the split between oil, char, and gas. Fixed bed reactors, with their long residence times and steady-state heat, tend to push more of the tire's mass towards solid char. In contrast, fluidized bed and rotary kiln designs, running hotter and with faster material turnover, favor higher oil yields. The numbers bear this out. Industry data shows that fixed bed reactors typically deliver around 45% oil by mass, with the balance split mostly between char and non-condensable gas. Fluidized bed pilots operating at higher temperatures and shorter residence times have reported oil yields as high as 63%. These differences are not just academic. Each percentage point of oil versus char shifts the plant's revenue model and downstream handling requirements. Oil itself is energy-rich, clocking in at 42 megajoules per kilogram, but its market value depends on purity, sulfur content, and blending requirements. Char, dense in carbon but high in ash, finds use as a solid fuel or as a feedstock for further upgrading, but commands a lower price unless refined. Process engineers track every variable, including temperature, feed rate, and particle size. They know that even a small change can tip the yield balance. In a 2022 retrofit, confidential mass balance sheets from a fixed bed line showed a consistent 45% oil yield, but with sulfur above 1.5%. When the plant trialed a fluidized bed system, oil yield jumped to 63%, and sulfur content dropped below 1.2%. That single data point, backed by weeks of trial runs, was enough to justify a full-scale investment in new reactor technology. The choice of reactor is not just a technical matter. It is a profit calculation, a logistics challenge, and a commitment to a particular product slate. Every plant's mass balance sheet tells the same story: how the physics of heat and time translate into barrels of oil, tons of char, and the economics of tire recycling at scale. Inside the Lab E, the journey from raw pyrolysis char to market-ready recovered carbon black is measured in test cycles, not in days. The raw material straight from the reactor arrives with 12% ash and an iodine number hovering around 35 milligrams per gram, well below the threshold for high-value elastomer applications. The chemist's logbook fills with a steady record of failures and incremental progress. Each batch is weighed, milled, and fed into the activation furnace. Temperatures climb above 900 degrees Celsius, oxygen levels are tightly controlled, and the clock starts. Every hour in the furnace is a gamble. Too little, and the ash remains stubbornly high. Too much, and the carbon structure collapses, losing the surface area needed for performance. Between furnace runs, samples are drawn for BET surface area and iodine number testing. The difference between a pass and a fail is often just a few milligrams or a fraction of a percent. One entry records a breakthrough, a batch with ash below 2%, and an iodine number pushing 70 milligrams per gram. The lab celebrates, but the process is far from routine. Each run is followed by chemical washing, filtration, and drying. steps that demand vigilance to avoid cross-contamination or residue buildup. Quality control is relentless. ASTM modulus tests, particle morphology checks, and surface chemistry analyses are repeated until the numbers are consistent. Only then does the material move forward, ready to compete with commercial N-series carbon blacks. The capital intensity of this workflow is visible in every corner: custom reactors, automated filtration lines, and racks of calibration standards. For every ton of recovered carbon black that meets specification, dozens of samples have failed. The margin between commodity filler and a premium product is set in the lab, one test at a time. Fire risk is a constant shadow in tire recycling plants, where the combination of fine rubber dust, textile fibers, and residual oils turns every pile into a potential ignition source. Stockpiles are strictly limited in height, and operators use thermal cameras to scan for hotspots, logging temperature readings at regular intervals. When an anomaly appears, an unexpected rise in surface heat, or a cluster of readings above the 60 degrees Celsius mark, protocol demands immediate intervention. The June 2021 dust fire, captured in emergency logs and dashboard screenshots, forced a complete overhaul of storage and turnover procedures. The incident began with a routine shift, but within minutes a small plume of smoke triggered a site-wide alarm. Response teams contained the blaze in under 2 hours, but the review board's findings were unequivocal. Stockpile turnover frequency doubled, and a new layer of thermal imaging was added to the daily checklist. Dust and fiber are not the only hazards. Pyrolysis and grinding lines generate a spectrum of airborne pollutants, particulate matter, volatile organic compounds, sulfur dioxide, nitrogen oxides, and acid gases. Each plant must deploy a chain of control measures: cyclones for coarse dust, baghouses for fine particulates, wet scrubbers for acid gases, and activated carbon beds for residual organics. At the core, a thermal oxidizer operates above 850 degrees Celsius, with a mandated residence time of at least 2 seconds to ensure destruction of polycyclic aromatic hydrocarbons, dioxins, and unburned hydrocarbons. Continuous emissions, monitoring systems, track carbon monoxide, nitrogen oxides, sulfur dioxide, and total organic carbon in real time, feeding data to a central dashboard. If any reading approaches a regulatory limit, automated alarms trigger corrective action or a controlled shutdown. Environmental engineers log every intervention and exceedance. Knowing a single out-of-spec event can trigger regulatory review or community complaint. Recent plant records show repeated sulfur dioxide and polycyclic aromatic hydrocarbon spikes traced to feedstock mix and incomplete scrubbing, which prompted internal audits and external mandates for equipment upgrades. In this environment, safety and compliance are not optional. They are the price of continued operation. The cost of failure is measured not just in fines or downtime, but in public trust and the plant's license to operate. Profitability. In tire recycling is never a fixed equation. It is a moving target shaped by the mix of tires entering the gate, the fees paid for intake, and the value of every output stream. Operators track a sensitivity chart, sometimes called a waterfall, that lays bare how each input can swing the internal rate of return from healthy double digits to deep in the red. For most high-volume plants, the business starts with a negative feedstock cost, being paid to accept old tires, often by the ton. In regions with strong extended producer responsibility, gate fees can make up half or more of total revenue, insulating plants from weak product prices. But the real volatility comes from the feedstock itself. A clean stream of passenger car tires, known as PCR, runs smoothly through the line with low steel and fiber content, high rubber yield, and minimal pre-processing. Financial models show that a PCR-dominant feed can boost the internal rate of return by as much as 12%, thanks to faster throughput and lower maintenance. On the other hand, heavy off-the-road tires, known as OTR, like those from mining or construction, bring thick steel belts, dense fiber, and unpredictable geometry. Plants forced to process a high share of OTR tires face slower lines, more frequent jams, and higher tool wear. In some scenarios, the internal rate of return drops by 3% or more, with downtime and extra labor erasing the margin. Product revenue brings its own swings. Crumb rubber, steel, pyrolysis oil, and recovered carbon black each have their own price cycles, but credits for carbon reduction or renewable fuel can tip the balance. In a strong policy environment, these credits add a premium to every ton processed. But when output prices soften or credits are delayed, plants lean harder on gate fees just to break even. The difference between a profitable and a marginal operation often comes down to how well managers match their feed mix to their equipment and how quickly they can adapt when the market shifts. Every hour, more than 40,000 tons of tire waste accumulate worldwide. As climate policy tightens and raw materials grow scarce, the real test isn't technical. It is whether recycled rubber and recovered carbon can truly replace the old supply chain. The circular economy isn't theory anymore. It is a global race, and the clock is already running. Share your thoughts on the future of tire recycling below.